get ready with your screen. Okay, so Harsha Nagarajan, our next speaker, is a staff member in Los Alamos National Lab in the Applied Mathematics Group. His research interests lie in global, stochastic, and nonlinear optimization, primarily applied to energy system applications. And he is going to present his paper, Algorithms for Mitigating the Effect of Uncertain Geomagnetic Disturbances in the Electric Grids. Okay, so Harsha, the word is yours. Harsha, we cannot hear you.
Yeah, okay. I think I unmuted now. Can you hear me now?
Yeah, we can hear you now.
Excellent. Can you see my screen too?
Yes.
Excellent. Okay. Thanks, Lina. Thanks for the introduction. And this is probably the only talk from what I could see in the titles of the PSCC program that is related to this geomagnetic disturbance problem in electric grids. Which kind of, I guess, makes it interesting. Okay, so this today I'll be talking about the algorithms for mitigating the effect of uncertain GMD in electric grids. So this was primarily the work of our visiting student from Michigan Ann Arbor last summer, Minseok, and with Russell Aitlano. Okay, the outline is I'll introduce the GMDs and the associated geomagnetically induced currents, the GICs. How do we model those? And then get into the mathematical model, which is based on the distributionally robust optimization approach. And then a solution approach, which is an accelerated CCG based algorithm, and numerical experiments on the test cases, which are specifically designed for the GMD studies. Okay, the background on the GMD is that geomagnetic disturbances, or GMD, is basically nothing but the changes in the magnetic field, which is caused primarily due to the space weather. In this case, it would be basically due to the solar wind particles. When they interact with the Earth's magnetosphere, there is an electromagnetic field which is created, and this electric field around the Earth's surface is what we call as an E field. As you can see in the right side of the right side figure of the United States map here, the magnitude and the direction are what really are used to quantify the electric field, as you can see in this heat map here. So these geomagnetic disturbances can create a lot of issues, and particularly of interest for us is basically the issues it can create for the bulk power systems. So the negative impacts of the geomagnetically induced current due to GMDs is that it can cause current distortions, hotspot heating of transformers, transformer windings, and half cycle saturation of transformers, and increased reactive power in the grids. So eventually all these causes can basically lead to an unstable grid, and also potentially lead to a cascading failure and a blackout. Historically, these events, though are not very frequent, do have a very high impact. In 1989, it had a very big impact in the hydrocubic system with just an 8 volt per kilometer electric field, which led to a 9-hour blackout. And as recently as last year, as you can see in this article, Venezuelan government blamed electromagnetic attack for a nationwide blackout. So it seems to be an important issue which can occur, even though it's not a very frequent event. So, and in fact, even Department of Energy also recognizes this as a high impact, low frequency event risk for the North American bulk power system, which is primarily of risk for the transmission system, part of the power grid, and which is what we will be focusing on in this talk. How do we mitigate the negative impacts of the GICs? In order to do this, we need to understand and improve the Earth conductivity model to estimate the E field accurately. And for this, there is a separate area of research which people are working on, coming up with the best representation of the electric field. And once we do this, there has to be an improved GIC calculation method. And even this was basically given in the NERC application guide in order to compute GICs quite accurately. And given this, it is about establishing mitigation actions that hedge against severe GICs, and which is where primarily our research lies in. So in the literature, there has been numerous papers which have been written, especially to handle the GICs through a certain set of mitigation actions. One of the popular ones have been to install blocking devices, and typically these are expensive devices, and it is about how do you optimize and place them in the grid optimally to reroute the GICs to the ground instead of burning the transformers. And other option is also looking at the transmission switching. This is something which we looked at in one of our initial papers in 2017, and later, of course, by the group with by Overby, they also looked at transmission switching as an option for large-scale power grids through some heuristic approaches. And then we also looked at modeling GICs as an uncertain electric field, and with just like any other natural hazards, even a GIC can be basically uncertain, as there is only a time scale of around 8 to 10 minutes within which they have a prediction of this is there is going to be a potential electric field which would be created, but then an exact measure of the magnitude and direction is going to be very hard to have. So considering that we model this uncertainty, our research in this paper looks at how do we control the transmission components such as transmission lines, transformers, and the existing generators in the network, and control the amount of load shedding. And at the same time, the challenge would be to handle the uncertainty of the magnitude and the direction of these electric fields. So to this end, let's look at a mathematical model of GIC. So here, the modeling of GIC is something what we pretty much follow what is given in the NARC guide, and I'll just go over that. So any electric field can be represented with respect to its magnitude and its direction, as I mentioned earlier. And typically it is decomposed into an eastward and a northward direction. As you can see, the Xi tilde eastward and the Xi tilde northward direction are the two parameters based on which we can model the electric field. And given these eastward and northward direction values, we have an induced voltage source which are also functions of the length of the lines in the grid. And once we have the electric field and the voltage source evaluated, we can calculate the GIC induced current based on the DC power flow analysis, and that's a very standard DC constraint with the line switching option, because we will need to model that later. And here gamma L is the conductance of the line. So so this equation basically is a linear. It's actually nonlinear with the line switching option, but otherwise it's a linear constraint, which gives us the GIC current. So given the GICs now, we need to evaluate the effective GICs on a transformer. So to do that, what we do is we represent any power network in two layers, which is an AC power network, which is the regular quasi-static case, what we model as an AC power flow network. And there is also an associated DC power network, which is where the DC power flow happens or the DC currents due to the geomagnetically induced disturbances happen. And for that, we have a separate layer of network, which also models the transformers. So clearly the effective current evaluated is a function of the type of the transformer and the number of windings in the transformer, etc., and which is what we take into account here. And given this effective GICs, now we can evaluate the reactive power loss due to the GIC, which is what is the most problematic thing which is caused due to the GIC. And this again this whole evaluation based on the loss factor of the transformer and the voltage magnitude at bus I from the AC network. One can evaluate the reactive power loss using this equation. So as you can see here, this is again a nonlinear constraint for our reference later. So now let's get into the mathematical model. Here, basically, we are going to be modeling this as a two-stage distributionally robust optimization problem, or what we call as the DRO. The idea of the DRO is very standard, where you would be minimizing the worst case, you'd be minimizing an expected cost for the worst case probability distribution P, which lies in the ambiguity set D. So this type of modeling is very ideal when it is very hard to estimate a probability distribution, which is ideally done for a stochastic programming approach. And due to the lack of historical data, modeling probability distributions can be very hard, and which is exactly why we take this DRO approach, which is indeed the case with this problem of GMD, as we know that these are low frequency, there are only one or like maybe 2 to 3 events in the history, but then we have some data, but not enough data to model it as a distribution. So hence we take this whole two-stage DRO approach. And once we write it up as a DRO problem, and also another motivation is that it's not as over-conservative as a robust optimization approach. So that's also another motivation, which is a standard thing for a DRO. So now for the first stage of the problem involves the switching decision of the network. In this case, the switching can be lines, transformers, and generators. Here, the generator switching need not be confused for the unit commitment setup, as here we are only looking at the quasi static case where we don't do any time extension of the formulation. That is something which we are right now working on, but then that's the next step after we finish this problem. So then Y represents the dispatch decision, which is all the power flow variables, load shedding variables, and the allowable reactive power loss in the stage 1. And the AC power flow constraints, which is the full nonlinear non-convex equations. And here the objective is to minimize the generation costs and the penalty costs due to the load shedding. So this is where we take the decision actions in order to mitigate the, or in order to hedge against this uncertainty which is going to be appearing. And once the GMD event appears, let's look at how we model this uncertainty here now. Psi tilde, as we saw earlier, can be parameterized using the psi eastward and the psi northward direction of the electric field. So given in this two-dimensional space and the fact that the data comes in this form where the worst case magnitude bounds the sum of the squares of this eastward and the northward direction, the underlying ambiguities, the underlying support set or the uncertainty set can be modeled as a half circle. So which is what we have, we can see in the figure on the right side. And here is a half circle support set. And typically having, though this is a convex support set, having an uncertainty set with infinite extreme points can be a bit cumbersome to handle from the algorithmic perspective. And hence we do an inner approximation using a polyhedral support set. So, and this polyhedron can be a pentagon or a hexagon or a triangle or multiple types of this. So we observed that doing a pentagon approximation is fairly good enough polyhedral approximation for this inner approximation for this half circle support set. So we just go ahead with that inner approximation from now on. And the reason I also have a triangle support set will become a bit clear later. So here, what does any point in the support set mean is that it can be looked at as a future uncertain scenario, which can be due to a GMD, which is given by its the value of the eastward and the northward direction of the uncertain parameter and the magnitude of the GMD. So this is what any point in this support set means. And the underlying ambiguity set is, of course, parameterized with these uncertain parameters, mu e and mu n, and with the ambiguity set as shown in the figure. Okay, now once the actual GMD event appears, or once it actually happens, now there is a damage in the grid. And how do we hedge against this damage is what is going to be taken care in the second stage problem. Here in the second stage, the decision variables are the reactive power losses due to GIC. So we basically decompose the problem in a way where the whole AC power flow and the AC network is in the stage 1 with the switching decisions, and the second stage is where we take the corrective actions. And is where we basically verify if the corrective action given by stage 1 is good enough to handle this worst case GMD scenario, and which is what we are basically modeling with the GIC constraints, which are also nonlinear and non-convex. And here the objective function is to minimize the damage due to the GMD. So solution approach, this is a two-stage DRO problem with nonlinear and non-convex constraints, binary variables. So it has pretty much every possible complexity of optimization in one problem. So now we obviously have to simplify it. So we apply the convex relaxation approach. We take the SOCP relaxations from Kochuk et al. For the AC power flow equations. We apply standard convex relaxations for the GIC constraints, and we reformulate that problem into a convex DRO problem. So now that it's convex, it is guaranteed to produce a lower bound to the original non-convex DRO problem. And since the recourse problem now becomes convex after all the linearizations, we know that and with the finitely number of many extreme points for this polyhedral support set, we know that the worst case uncertainty scenario has to be one of these extreme points for a convex recourse problem. And which is exactly what we do in this by looking at strong duality, and we apply the column and constraint generation algorithm. I think Christina mentioned, gave a nice outline of this algorithm, so I will not get into any detail, but the whole idea is to dynamically generate constraints and the recourse variables in this algorithm, which is typically applied to two-stage RO problems. Here we apply it for the DRO, and this is a very standard approach which one can apply for a problem of this type, when you have a convex recourse, of course. But what we looked at was that there is a nice, interesting structure which can be exploited to speed up this algorithm in order to be able to solve on slightly moderately large scale networks. And the idea is as follows. As we saw earlier in the figure, that we could inner approximate the support set using a polyhedron. If we take the polyhedron with 3 extreme points, which would be a triangle support set, there exists a very nice closed form solution for this version of the support set, where the worst case distribution can be analytically rewritten, or it is basically a unique solution which you can just directly obtain by inverting the matrix of the probability, and then write this DRO model as an exactly reformulated monolithic reformulation into a single MISO-CP problem. Of course, it's still an MISO-CP, but then now we assume that solving an MISO-CP is better than solving a two-stage DRO with CCG algorithm. So solving this triangle support set problem directly using good solvers like Gurobi is much faster than applying an algorithm. So now that we have a triangle support set based solution, and since the support set is indeed a subset of the original polyhedral support set which we want to solve on, the solutions what obtained is indeed a lower bound from this solution, and hence we can update with a tight lower bound and with some warm starting strategies, and deriving a few valid inequalities based on just looking at simple logic based constraints for the topology of the network. We can speed up the overall CCG algorithm for a generic polyhedron. And this is true for any polyhedral support set, and decomposing, or in some sense tessellating it into a triangle support set and looking at the triangle solution and then applying it on a general polyhedron. And this seems to do really well algorithmically. So let's look at the results. We basically test on the 2 cases, which is the EPRI-21 and the UIUC 150 system, which are specifically designed for the GMD studies. UIUC 150 system, of course, comes from the Texas A&M University's ORB's data set. And the electric field data here is basically we test on multiple magnitudes of electric field and with multiple mean values, and we create around 50 instances for the numerical testing purposes. And
Harsha, you have about
time?
Like 1 minute more.
Okay, thanks. I'll wrap it up. Here, as you can see, basically the thing is, if the points lie under the blue line, our algorithm is better, and which is what exactly happens while comparing with classical CCG algorithm with our accelerated CCG based on the analytical reformulation of the 3 extreme point support set. So that's the relaxed DRO problem. And then we try to come up with looking at how does our DRO solution perform. And for this, we basically compare our approach with just looking at the mean value, and which is just a deterministic model, and without taking any corrective actions. And one thing I would like to mention is that this DRO approach with the relaxed model, as we know that when we apply convex relaxations, it may not necessarily lead to practically meaningful solutions because they may not be AC feasible. So this is some work which we have added after the PSSC paper, which we submitted, that here now once you add this whole nonlinear non-convex GIC and AC power flow constraints, the extreme point may not necessarily be the worst case scenario anymore, and it can be some interior point. So we basically sample this whole support set region with 5,000 points, and we try to solve this for a given mitigation action from the relaxation formulation. So this is basically like a set of nonlinear programs which can be solved using IPOpt, and this is pretty fast. So what do we see from this is that the operation cost, as you can see, if hedging against the uncertainty using the DRO approach leads to much lesser operation costs. More than the operation costs, I would say, as you can see in the bar figure in the bottom right, that the penalty cost for the load shedding can be way lesser as you're actually planning for the uncertainty pretty well. And also the whole reactive power losses can be quite low in the network by modeling through the DRO approach. And we also have simplifications for the larger system too. Thank you, and I'll take questions. And here is the paper link. Sorry, I'm done.
All right. Okay. Yeah, you were actually wrapping up. Sorry about that. I didn't mean to come there in the end. Yeah. So I think we have like time for maybe one question before we get to the last speaker here also. So there's a question, there's a comment in the Q&A, which is comment, there is a second GIC paper I've seen. Yesterday there was one with the title Data-Driven and Transmission Network Parameters for GIC Modeling. So this was, I guess, just an FYI from Marcin Poyampalo. From Patrick Ponce-TC, there's a question: installing series capacitors on long power lines seem to solve the problem of DC components. It seems that Hydro-Quebec did that, and now they don't seem to worry too much about, Could you confirm this?
Yes, thanks, Patrick, for raising that point. So there has been, in fact, people have been talking about installing series capacitors to be able to handle this issue of DC components. And here, the whole point of what we were trying to look at here is that, can we just use the existing network controls, control actions just based on the pure transmission line switching or switching certain generators or transformers, and can we just reroute the GICs without installing any additional devices, was kind of the real motivation behind this work. But this is something which we also want to look at, where you actually can install series capacitors and control this issue.
Cool, thank you. So there is another question from Dan on the SOC relaxation and whether that would be cheating a lot. I would just recommend, if you could type the answer of that into the Q&A, that would be great, so that we can get started with our last speaker of the session. Okay, thank you. So yeah, and I just want to acknowledge here that we are a little over time. We had some technical difficulties in the beginning, but I hope that our attendees here will be able to stay maybe a little longer, so we can just have the time to also see properly Laurel's presentation and also have her answer some